Section 4.7 Exponential and Logarithmic Models. In this section, you will model the exponential growth and decay, including half-life, using Newton's law of cooling, and use the logistic growth model. So let's start with the exponential growth and decay. In the sciences, things that grow exponentially fast appear in many applications. In general, the model for exponential growth looks like this. A of t is equal to a sub 0 e to the power of kt, and a of t means the amount, a sub 0 means the initial amount, and t means the time, k is the growth or decay constant. K greater than 0, then you can say that it is increasing, and k less than 0, then it is decreasing. So whereas k is a real number. Okay, example 1. A population of bacteria doubles every hour. If the culture started with 10 bacteria, come up with the function that models this exponential growth. So every hour, so meaning t is equal to 1 here, and if we have, let's say, a table t and a of t, so at the beginning it started at 10, and then after the first hour says it doubles, so it's going to be 20. Second hour, that's going to be 40. The third, it doubles, so it's going to be 80. So we know that here it started at 10, so we could say, we could write our equation. A of t is equal to 10 e to the power of kt. That was the initial value. A of 0 is equal to 10, and let's use this second. At the end of the first hour, it was 20. T is 1. Then here with this, we can solve for k. So we divide both sides by 10. This is now 2 is equal to e to the k. And to solve for k, what we do is ln both sides. Ln of 2 is equal to ln of e to the k. Now ln of e to the k is just simply k, so ln 2 is equal to k. So we're going to use that to write our equation. A of t is equal to 10 e to k is ln 2, ln of 2t, and that becomes our a of t is equal to e to the ln 2 is simply equal to 2, that is 10 times 2 to the t. So that is the answer. Okay, next one, half-life. All radioactive isotopes decay exponentially. A key trait is that a given isotope has a consistent time to reduce by half. We call this as half-life. The formula for half-life is as follows: T equals ln of 2 over k, or also we can rewrite this as k is equal to negative ln of 2 over t. And just like for example number 2, the half-life of carbon-14 is 5,730 years. Express the amount of carbon remaining as a function of time t. So k is equal to negative ln of 2 over, the time is 5,730. So this is our k. And that is approximately, when you use a calculator, is equal to negative 1.2096 e negative 4, and that is approximately equal to negative, so this is negative 4. You can move the decimal 4 places to the left. That's 1, 2, 3, 1, 2, 0, 9, 6. So this is our k. So now we can write our equation. A of t is equal to a sub 0 e the power of negative 0.000120996 t. That is the amount of carbon-14. Okay, that's it. Next one, we will use the following formula from chemistry to help us date the age T of fossils using a technique called the carbon-14 radioactive dating. So T is equal to ln of R over negative 0.000121, where R stands for the given percentage of carbon-14 in an object. For example, a bone fragment is found to contain 20% of its original carbon-14. How old is the bone? So R is 20%. So meaning that is equal to 0.2. Then age of the bone, that is T is equal to ln of R is 0.2 over negative 0.000121, and when you divide that, then the T is approximately equal to 13,300 years old. Okay. Next one. Newton's law of cooling. The temperature of an object in surrounding air with temperature T will behave according to the formula T of T is equal to A e to the power of kT plus Ti, where T is the time, A is the difference between the initial temperature of the object and the surroundings, and K is the constant, the continuous rate of cooling of the object. And let's use that formula to answer this example number 4. A cheesecake is taken out of an oven with an internal temperature of 165 degrees Fahrenheit and is placed into a 35-degree refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. How long until the cake cools to 70 degrees Fahrenheit? How long? So we're gonna solve for the time T. So we have here the initial temperature at 165 degrees Fahrenheit. So we can say that T0 is equal to 165. So we can use that to use our formula. So it was 165 is equal to A e to the power of k times 0 when t is 0 plus $35. Place in the 35-degree refrigerator. So this is our T. So here we subtract 35 both sides. That is gonna be 130 is equal to A k times 0 is 0, E is 0 is equal to 1. So A is equal to 130. And then says after 10 minutes, so you can say that at T10 the cheesecake has cooled to 150 degrees Fahrenheit. So this is equal to 150. So let's do the same thing here. So 150 is equal to A E K to the 10th plus 35. A is now 130. Then subtract 35 both sides. That is 115. And then divide both sides by 130. Then here e to the power of k times 10, and to solve for k, we ln both sides. Ln e to the power of k10 is simply equal to just k10 or 10k. This is ln of 115 over 130. And divide both sides by 10 to solve for k. K is approximately equal to negative 0.0123. Okay, so we can say that T of T is equal to A is 130, E to the power of K is negative 0.0123 T plus 35. Then our question is how long until the cake cools to 70 degrees Fahrenheit. So here is 70 is equal to, now we're solving for t, e to the power is negative 0.0123 t plus 35. Then if we subtract both sides by 35, so this is 35 is equal to 130 e to the power of negative 0.123. Sorry, missing a 0 here. Then divide both sides by 130. And then ln both sides again. Ln e to the power of negative 0.123 t is now simply negative 0.0123 t. And now we can solve and divide both sides by negative 0.0123, and you will have t is equal to 106, approximately equal to 106.68. So that means it will take about 107 for the cheesecake to cool to 70 degrees Fahrenheit. Okay, it will take 107 minutes. All right, next one, logistic growth. The logistic growth model is f of x equal to c over 1 plus a e to the power of negative bx, where c over 1 plus a is the initial value, c is the carrying capacity or limiting value, and b is a constant determined by the rate of growth. And let's solve this last example to use that formula. Example number 5. An influenza spreads throughout LMC Brentwood according to the logistic growth model. Says there's 1,000 people at LMC Brentwood in a given day, and at day 0 was 1 person sick, so f of 0 is equal to 1. Finally, let's say that the biology department was able to figure out that the growth rate constant is 0.6030. Now, the question is how many people will have the flu after 10 days, and then how many people will have flu as time goes to infinity. So when t is equal to 0, we could say that c over 1 plus a is equal to 1, since f of 0 is equal to 1. And then if you multiply this both sides, cross multiply 1 times 1 plus a is 1 plus a, and we have the initial value of 1,000 is equal to 1 plus a, and if you subtract 1 both sides, a is equal to 999. And then we want after 10 days. So f of t is equal to the initial was 1,000, 1 plus a is 999, e or b is 6.6030, negative 0.6030x. and this is approximately equal to 293.8, and because the actual number must be a whole number, a person has either had the flu or not, we round it to 294. And in the long term, the number of people who will contract the flu is the limiting value C is equal to 1,000. Take a look at this graph here. So day 0, there was 1 case. After 5 days, 20 cases. After 10 days, you have approximately equal to 294. And on day 21, you'll reach the maximum of 1,000 cases. Okay, that's it. And this is section 4.7. And if you have any questions, please let me know. Thank you.